Coming to the mechanism of addition elimination type of reaction. See, in this, the first step is addition. In fact, it is the slow step of the reaction or the rate determining step. See, here in this case, the nucleophile attacks the carbon to which the halogen atom is attached. So, first addition. Now, this is a rate determining step or the slow step of the reaction. Okay. We get different resonance structures, but the overall thing can be given as this, a carbene ion, because anyway we get a negative charge here and this just goes on delocalizing, right? So the overall thing or the resonance hybrid can be given as this carbene ion. It is of course called Mesenheimer complex or Mesenheimer intermediate. Very important. Now this carbene ion of course is stabilized by this electron withdrawing group. Okay, now the second step. I mean the elimination step, which of course is fast. See, in this step, this just goes off. Cl minus goes off, and we will get the final product. Okay. Now this, because we are still in basic medium, this OH minus abstracts the H plus. Now we get a phenoxide ion, as I said, because we are still in basic medium. Now to this, when acidic hydrolysis is carried out with this, we get the final product. Of course, here itself, we got the product, but because we are still in basic medium, I've taken these two steps. Okay. Now let us see something about this mesenhymer intermediate or mesenhymer complex. Let me take nitro in this fashion. Towards this carbon, when the bond moves, we get this. A bond here, a negative charge here, this thing as usual. A bond here, then this. Giving the different resonance structures. First one, now the second one. Look at what happens now. The negative charge delocalizes. A double bond here, then this becomes O minus, O minus again, a positive charge, then this. This is a third one. Now again, towards this carbon. A negative charge, this is of course the fourth resonance structure. Now these all, if you look at the structures, so this is where we have started with our negative charge, and this is where we have actually ended up. So now all these resonance structures can be summed up or can be given in the form of a resonance hybrid. This is what we have taken. Okay. Now, considering the stabilities of these resonance structures, I mean, among 1, 2, 3, and 4, which one is more stable actually makes it more interesting. You know, the third one is most stable. But why? You know, this is the only resonance structure where you got negative charge on oxygen atoms which are highly electronegative, which are supposed to have negative charge. You know, a negative charge has to be there on the highly electronegative atoms, and a positive charge has to be there on more electropositive one or less electronegative one. But see, here you got a negative charge on carbon. Even here also it is there on carbon. Even here also it is there on carbon. But the only resonance form where you got negative charges on the highly electronegative oxygen atoms is the third one. So this is the most stable form. The remaining, I mean, 1, 2, and 4, less electronegative. Carbon has a negative charge. Therefore, they are less stable. Okay. This is all about addition elimination mechanism. Now, let us go for elimination addition mechanism. Okay. Example. Let us take a bromobenzene. When this is treated with sodium amide, we know that amide is a stronger base. Of course, a strong nucleophile also. Okay. With sodium amide, we get two products. This one and this one. Very interesting. See, the first one is formed when the substitution has taken place at the carbon to which the halogen atom is attached or the leaving group is attached. Substitution at the carbon to which leaving group is attached. You know, this kind of a thing is called ipso substitution. Okay. Now the second one. This is quite interesting. See, here the substitution has occurred at the carbon adjacent or next to the carbon to which the leaving group was attached, was connected. Substitution at the carbon next to the carbon to which leaving group is attached. Now, this is called sign substitution product. Okay. Ipso, of course, is common, but sign is interesting. To know what has happened, let us see the mechanism. See, in the first step, nothing but the elimination step. Now, in this step, see the NH2 minus. It is acting as a base. Look at this. The pair of electron is given to a proton. So, we can say that it is acting as base. And see, as and when the proton is abstracted, this, of course, goes here to the carbon. Okay, now. We have actually eliminated ammonia. Now, in this step, as and when this comes here, this one goes off. We get a very interesting intermediate called benzene. Okay. So this benzene intermediate is highly unstable. Now this immediately undergoes addition in the second step. The first step is elimination, and now it is addition. Now this benzene is attacked by the nucleophile. Now see the same NH2 minus. is acting as a nucleophile. See, it may attack this carbon or this carbon. Let this be the possibility number 1, this be the possibility number 2. Okay. See, in the first possibility, let us see what happens. We get negative charge here in the first possibility, because as and when NH2 minus attacks this carbon, this will go here. So that is how we get this negative charge. Okay. Then the second possibility. Say in this case, as and when the NH2 minus attacks this carbon, the bond goes towards this carbon. Consider the black one. Look at this. So it allows attack in 2 ways. Now you get NH2 here. Got the products almost. Now considering the first one, take the ammonia again. A hydrogen is abstracted. H plus is abstracted, and we get the ipso substitution product. Considering this, we get the sign substitution product. Okay. So this is how in the first step we get benzyne intermediate. And this benzyne intermediate is attacked by NH2 minus, which is acting as nucleophile in 2 ways to give rise to 2 different products. One is ipso, the other one is sign substitution product. Okay. Now let us take some interesting properties of aryl halides or haloarenes. See, when 2 aryl halides are treated with sodium metal in dry ether, just as in Wood's reaction. Of course, here we have taken two aryl halides. We get biphenyl or a diphenyl. Along with that, of course, sodium halide. So this reaction is called Fittig reaction. Okay, Fittig. Now, if suppose we take one aryl halide and one alkyl halide. In the presence of dry ether again, we get alkyl benzene. Along with this, we get sodium halide. Now, this is called Wood's Fittig. Interesting. You got alkyl halide, you got aryl halide. Only alkyl halides is Woods, only aryl halides is Fittig. Alkyl as well as aryl halides is Woods Fittig. Right. Now let me also give your Woods reaction. We get a symmetric alkane, and this of course is Woods reaction. So three very important reactions. Woods Fittig, Woods Fittig. Now, see when iodobenzene is treated with a copper powder, we get biphenyl. Or a diphenyl. See, this is called Ullmann's biaryl synthesis. We got biphenyl, nothing but biaryl. Next. See, when benzyl chloride is treated with urotropin, nothing but hexamethylene tetramine, we get benzaldehyde. Or you can say benzene carbaldehyde. Now, this again is a famous named reaction called Somerlet reaction or Somerlet oxidation. Let me also give you the structure of this urotropin. Okay. CH2 taken 6 times N4. Okay. So this is urotropin. See, when bromobenzene is treated with lithium metal, in the presence of dry ether, we get phenyl lithium. Okay. Along with this lithium bromide. Next. Formation of Grignard reagent. Phenyl magnesium bromide. Nothing but Grignard reagent. Then chlorobenzene with magnesium. Now this reaction is carried out using dry tetrahydrofuran. This one. Of course, we get phenyl magnesium chloride. Okay. Again, a Grignard reagent.